Okay, calculus. Today and tomorrow we're going to be looking at the cross product, which is the second type of multiplication of vectors. We looked at the dot product the last 2 days before now. We use this for magnetism and torque. So some of you have talked about torque before in the shop and in science. We have a three-dimensional type of situation going on here, which we don't with the dot product. Two vectors in three space. The cross product results in a vector perpendicular to both of the vectors given. Okay, and we'll talk about the direction. It comes from a right-hand rule. And this result is the normal to the plane containing the two vectors. So let's have a look at a little diagram for a second. If you have a plane that's supposed to look like a plane, and you have two vectors and you find the cross product, the cross product would be perpendicular to both of those other two vectors. A cross B. So if we have A and B, B, and the vector from those two, A cross B, would look like that. And a normal is a perpendicular vector from a plane, and it would also look the same in the same direction as A cross B. We use a right-hand rule, and I'll give you a diagram for that in a second, but we would have your first finger, your pointer finger, I'll call that pointer, would go along the first, so this is your right-hand rule, right hand. So we're going to try this together. Pointer finger goes along vector A, your middle or square finger goes along B, and the resultant is your thumb. So for this particular diagram, if I put my pointer finger along A and my middle finger along B, my thumb is going upwards. So my cross product would be in the upwards direction on this particular diagram. Okay, so here we have some definitions here. We have the cross product of A and B is a vector. Its magnitude looks rather similar to the dot product, but it's the magnitude of A, the magnitude of B, sine the angle between them instead of cos the angle between them when they are placed tail to tail. It is true that the cross product is perpendicular to both A and B. And we find the direction from a right-handed system. I don't know if this particular diagram is hurtful or helpful, but it is on the handout notes that are at the top of this unit if you wanted to print them off. That's the right-hand rule, pointer finger. Along the first vector, middle finger follows the second vector, and your thumb is the resultant, the cross product. Okay, we said this is applied like in torque. So if we were to turn a wrench, that bolt is going to go into the blackboard or out of the blackboard. The righty-tighty rule comes to mind for those of you that have used a wrench. So we have this axis of rotation is on the bolt here. And I've got this lever arm, this wrench, and we could draw that as a vector. So here is this pivot point, and we've got a vector. The longer this wrench is, the better the job is going to be, by the way. And I'm going to do a counterclockwise force. Okay. So say that I am pushing on my wrench like this. Those of you that can picture this, which way is that bolt going to turn? It is going to turn to the left. So, by the way, bolt turning to left. Picture yourself doing this. We have the lefty-loosey principle. So this bolt should come out of this page and fall on the floor. To think of it as a vector, I'm going to redraw this. So I have my wrench, I have my force, It's supposed to look the same as the force. And if I put my fingers in position, my forefinger goes along the wrench. My middle finger follows the direction of the force. And my thumb should demonstrate which direction that bolt is going to go. Okay, so the wrench, there's the bolt. We have the wrench, and we have the force acting on it. And I've got to use a right-hand rule, so I've got the wrench, the force acting on it, and my thumb is coming out at you, so that bolt should be loosening and falling off the page at any moment. This turning effect would depend on the length of the wrench. If you've ever dealt with something stubborn, get a longer wrench. So it depends on the length of that vector technically. Or add a pipe if you just need to make it longer, that will change the length of that vector and the magnitude of the force. So oddly enough, I think some of you could produce a larger effect than I could. So you want both of those vectors to be high. And the angle between them would also make a difference. And we are talking about a cross product for torque. So by definition, the cross product. Make sure we have this written down. The magnitude of the cross product, because a cross product is a vector. But the magnitude would be the magnitude of the one times the magnitude of the other, sine the angle in between them, where theta is between 0 and 180 degrees. And it is assumed that A and B are tail to tail. And in the cross product, order matters for sure, because that will tell you the direction. Let's have a look at an example for a second. We have vector A has magnitude 10, and vector B has magnitude 12, and there is 55 degrees between them. So if I want the magnitude of A cross B, actually, yeah, let's just do the magnitude off to the side. Magnitude of A cross B would be 10 times 12 sine 55. So its magnitude would be, it's about 98.3. Okay. So A cross B, though, is a vector. So we could say it's 98.3, and then we need to give a direction for that. So I'm going to use my fingers. I'm putting my pointer finger along vector A because the order is A cross B. My middle finger along vector B, and trying not to break my hand, I realize that my thumb is pointing into the blackboard. So it's 98.3 into the blackboard or paper. Okay. Whereas B cross A, the magnitude would be the same because we have the same two numbers. We would just change the order. We would have 12 times 10 sine 55, and we would have 98.3. But this one, if I do B with my pointer finger, A with my middle finger, I am actually twisting my arm kind of backwards. My thumb is coming out of the board, and so out of the board or out towards you, some reference to direction, and I have the vector B cross A. With Cartesian vectors, I like Cartesian better than algebraic. Sorry about that. It's a little trickier. We could find the magnitude of each one of those, and we are capable of finding the angle between them, but it's much more interesting to use a formula. I can get this to show you. It's like the opposite of the dot product in so many ways. Dot product is A1B1 plus A2B2. To find the cross product, we have everything other than A1 and B1 for the first component, everything other than A2B2 for the second component, and so on. So you're going to need a copy of that in front of you. A cross B is A2B3, subtract B2A3. A3B1, subtract B3A1. A1B2, subtract B1A2. The proof of that is really interesting, but I didn't think it would be a great video. So let's do this one and find the cross product. So the cross product is going to be a vector. A cross B equals. So I need A2B3. So this is vector A, this is vector B, and the order does matter. A2B3 would be 1 times 3. I have to be careful. Subtract B2A3. 2 times negative 1. Comma. That's the horizontal component, or sorry, the x component. A3B1 is negative 1 times 1. Subtract. B3 is 3. A1 is 2. Comma. The y component. A1, which is 2. B2, A1, B2, 2. 2. Subtract B1, 1, A2, 1. All right. 3 subtract 3 add 3. 3 add 2. Oh, for Pete's sakes. 5. Negative 1 take away 6. Negative 7. And I am getting 3. Just going to check my numbers again for a second. A2, B3, A3, B2. I think I'm good. All right. So that takes some serious concentration to end up with the vector A cross B. There's another way to do this. If you are willing to do a shortcut, I'm going to just show you what we call down products, up products. You can always use this formula. It always works, but you have to get those A2, B3s straight. Down products, up products. It's doing the very same thing, just a slick way of writing it. So let's try this instead. All right. So vector A, I'm going to write it out twice. So this is vector A. 2, 1, negative 1, 2, 1, negative 1. Vector B, I'm going to write it out twice. 2, 1, 2, 3, 1, 2, 3. I know for my horizontal components, I don't have anything to do with A1, B1 for the first. So I get rid of that. I know for my last components, I don't have anything to do with A3, B3, so I'm going to get rid of that. So down products, up products. Down, once you've gotten rid of the outer 2, this would be a down product. 1 times 3 is 3. An up product would be 2 times negative 1. Down product. Negative 1 times 1 is negative 1. An up product. 3 times 2 is 6. One last pair. 2 times 2 is 4. 1 times 1 is 1. Notice in the formula we have in brackets there's subtraction going on. So I'm taking those up products, down products, and I am going to subtract. 3 take away negative 2 is 5. Negative 1 subtract 6 is negative 7. And 4 subtract 1 is 3. So we did the same thing, we've just written it in kind of a slick little way. Because I'm not there in person to see how you're doing, I'm going to walk through 2 more, and I'm going to show you a way of checking your answer as well. Okay, the first one I'm going to do is 3, 1, negative 2 cross negative 4, 3, 1. And we're going to check our answers by using the dot product. Example 1, if I want to find the cross product, let's do a bright color. I'm going to write this out twice, 3, 1, negative 2. 3, 1, negative 2, cross with negative 4, 3, 1, negative 4, 3, 1. The cross product would remove, come here, would remove the outer 2, and then down products, up products. So down would be 1, up product would be negative 6, down product would be 8, up product would be 3. Down product would be 9, up product would be minus 4. We would subtract. 1 subtract negative 6 is 7. 8 subtract 3 is 5, and 9 subtract 4 is 13. It is really hard to picture those vectors and whether 7, 5, 13 is perpendicular to both. But 7, 5, 13 is supposed to be perpendicular to 3, 1, negative 2, and also perpendicular to the vector negative 4, 3, 1. I'm going to check my answer by using the dot product. If it's true that it is perpendicular to each of those, then it would be true, first of all, that 7, 5, 13 dot, the first one, should be 0 if it's perpendicular. And also, 7, 5, 13 dot product, second one should also be 0. And then we know we've got the right answer. So the dot product, A1, B1 plus A2, B2 plus A3, B3. So I would have 7 times 3 plus 5 times 1 plus 13 times negative 2. I would have 21 plus 5 is 26. Subtract 26 is 0. Our answer was perpendicular to the first vector. Is it also perpendicular to the second vector? 7 times negative 4, A1, B1 plus A2, B2 plus A3, B3. Here's the dot product. I'd have negative 28 plus 15 plus 13 is 0. So it is perpendicular to both original vectors. We have found the correct cross product. Let's find the cross product of the second one just for practice. I know I'm going fast. So if I want the cross product of these two, I can write out the formula from before A2, B3 minus B2, A3 and so on. Or I can do up products, down products. So for this one, I would write out the first vector twice, 1 minus 6, 9, 1 minus 6, 9, and the second one below it, 3, 3, 2. I remove the outer 2 so that I've lined up my A2, B3s correctly. For down products, down on the top, up on the bottom, down product, the first one would be negative 12. The first up product would be 27. Down product, 27. Up product, 2. Down product, 3. Up product, negative 18. We subtract for the cross product. So I have negative 39, 25, and 21 as my cross product. To check my answer, it needs to be perpendicular to both. So I'm expecting that 1, negative 6, 9, dot product in order and dot product doesn't matter. The dot product to our solution should be 0. And I'm expecting that 3, 3, 2 dot product with our cross product is also 0 because it should be perpendicular to both of those. Okay, 1 times negative 39 And negative 6 times 25, and 9 times 21. Oh, can I do this in my head? Negative 39, subtract 150, and 189, plus 189 is 0. 3 times negative 39, plus 3 times 25, plus 2 times 21. So I have negative 90, negative 117, plus 75, plus 41. Oh, I have to check with the calculator just a second. What do you know? It's 0. So both of our vectors are perpendicular to the cross product, so we have found the correct cross product. Some good practice would be page 408, number 4 and 6.